All right, rotational kinetic energy. So we're actually going to figure out how rotational kinetic energy works based on examining what happens with translational kinetic energy as you watch an object follow a circular trajectory. So we'll have our XY coordinate system, and we will imagine we have an object that has some mass and has some velocity tangential. And ultimately it is tethered such that it executes a circular motion with a radius of r. Let's see, I like to color code things, so let's make r green. All right, so the kinetic energy of translation would look like 1/2 mv squared. But we know how to rewrite the velocity now, the velocity tangential, in terms of the angular speed. So if this has some net angular speed going around omega, now I want to move that m, then we can rewrite it as just, well, like this. And that means the kinetic energy will look like 1/2 mr squared omega squared. And I will call your attention to this part right here. So we've got the original equation, 1/2 mv squared for translations. Everything else we've done when we've changed from translational motion to rotational motion, we've substituted omega for v. So the omega squared makes logical sense when we're looking at kinetic energy of rotation. It leaves this term in the middle, which should have a meaning, something like mass, but like rotational mass. And in physics, we do have a separate name for rotational mass. So the rotational kinetic energy is what we call 1/2 I, which is the resistance to rotational motion. It's like the mass for rotation. It is called the moment of inertia times omega squared. And this means I for a particle, the moment of inertia of a particle, is mr squared. Okay, and again, we're going to map it out this way. Essentially, moment of inertia is rotational mass. It's resistance of an object to being rotated. We will learn in the next chapter about torque is equal to moment of inertia times alpha, which is the rotational equivalent of the second law equation, where we see again it's being used like mass. It is a resistance to being rotated, or being accelerated in rotation, perhaps I should say. All right, so that's what you do if you had a single particle. But I do want to talk about what happens if you have a system that consists of multiple particles which are attached to one another. So let's imagine something where here's the center of rotation. And we will arrange some masses around this point. And I'm just going to choose a somewhat arbitrary arrangement. We'll say that each one of these is a distance r away from that center point. So each one of those, we could calculate the moment of inertia for each one individually. It would just look like the mass of that particle times our distance from the center of rotation squared. And each one, in this case at least, is the same. So I total, the total resistance for a shape like this being rotated, would be the simple sum. And that is in fact the general rule. If you have particles, all you need to do is find mass of each and distance of center from the center of rotation to the mass for each one, and sum them all up. So at a Bayes superposition, it is the simple sum. Always nice. We like to see simple. Simple is good. All right, so for point masses, you would simply write that the total moment of inertia is a sum from I equals 1 to whatever your last particle is, mass of that particle, distance of that particle from the center of rotation squared. I should move that down further. One moment. So the ith particle, and then here distance to the ith numbered particle from the center of rotation. Okay, this is great if you're dealing with point masses, but the large part of what we're getting into now is dealing with extended objects, something that's solid throughout, like this thing trying to spin around one of its edges, or trying to spin around its spine, or trying to spin around its center of mass. We can imagine a shape like this is just made up of lots of little particles, a whole collection of particles, an infinite number of very, very small mass particles. So in the next step, we will take the logical step, and we will be thinking about moment of inertia for a continuous object being an integral of the distance from the center of rotation squared for a particular mass times that mass. So that's what we'll be up to next. All right, I think that's the end of this one. So we'll start getting into moments of inertia for continuous shapes next.